So we have introduced the notion of a resistive temperature sensor, right, which is a resistor whose resistance changes as a function of temperature. And we reviewed the concept of voltage divider, right, which is a circuit that does anything. And now, just like that, we're going to put them together. And the way we're going to put them together is we're going to take our battery. Let's say it's a 10-volt battery. And we will create a voltage divider out of two resistors. Now, this resistor here, which I'll put a circle around it, is our thermoresistor. It's this one, right, that we were holding on to before. This one here, I'm going to call R fixed. And by what I mean by fixed is it doesn't change. It acts like a regular resistor. Maybe it's 1 ohm, maybe it's 2 ohms. All right? Let's use the example in this case where it's 1 ohm. So we know this is 10 volts. We know this is 1 ohm. This value will depend on the temperature. And I think you see where this is going. I'm going to measure the voltage here, and I'm going to call that V sub T, right? Even though I'm drawing it out here, I hope you can imagine physically building this. All you would need is one battery or voltage source, a fixed resistance, and that thermoresistor you got, right? After building it on the circuit, you take your voltmeter, all right? To be clear what we're talking about here, right? You'll take your voltmeter, right? You'll take your voltmeter and you will measure the voltage across this resistor here, and we'll see what the display tells us. So this V sub T, right, is a display that we're looking at, right? Physical circuit. Well, what is the equation for this? Well, it's a voltage divider, right? Even though the symbols have changed, it's the same circuit. And so this V sub T is going to equal R sub T over R sub T plus R fixed times 10 volts. And so the output voltage here depends, right? The output voltage depends on this resistance, according to this equation, which is not too complicated an equation. But the resistance depends on temperature. And so therefore, this voltage will also be a function of temperature. And not in a way that we can't figure out, actually in a very, very specific way, right? We can in fact take this expression here and insert it into this, right? Which will create a slightly longer term here and a slightly longer term here. I want to emphasize, so this is a function, using a lot of colors here, of temperature. This is also a function of temperature, right? Using all my colors here. This we measure. This we measure. This we know. How do we know? Because you made it. I mean, you made it, so you picked a 1 ohm. This we also know. So this we know because we measured it. This we know, and this we know because we put it in. And so there's only one unknown in this equation. It's just this unknown. Just like this has just. So let's say we did it. And let's say you happen to measure, as an example, 5 volts, right? This was the measurement you got with your voltmeter. So now it's fair for me to ask you, what is R sub T? Well, 5 volts, to write it out, equals R sub T over R sub T plus R. Let me just use F for, well, let me put in the values. R sub T over 1 times 10. This happens to be in volts, right? This is in ohms. So what value of R sub T would satisfy this? You can tell by looking at it, right? That in this case, R sub T must be equal to 1 ohm, right? If this is 5 volts, we can calculate what R sub T is. Now, of course, I chose that to be the same thing here, right? But here, we were circuits class. But here, we're in instrument class. And so what we're doing is we have made this device. We have measured the voltage here, and we have realized that the resistance is 1 ohm. Now, we're not fully done yet, because obviously my next question is, well, what's the temperature? What's the temperature?
25 degrees.
Right, and so we would go to this equation. In this case, it's almost not necessary. But let's go to this equation. So 25 minus 25, well, that's 0, right? Oh, sorry. I'm doing it the other way. We know that this resistance is 1 ohm, right? So what value of T1 would satisfy that? And that is satisfied when the temperature is 25 degrees C. I went through that quickly. We can go through that again for another example. But now you know that the room is 25 degrees C. Right? Yes?
I have a question. Consolidating this image with the original one that we started off with the sensor, the wire, the circuit.
Exactly.
Because they seem more integrated than like linearly separated.
All right. You want to consolidate this with this.
Yeah.
Let me do one more example, and then we will consolidate this with this. All right? So you're quite happy with what you've done here. You're measuring the voltage here, right? We have a display, right? We're measuring the voltage, and suddenly you see that the voltage changes. So the voltage goes from, getting a little bit messy here, but follow along. The voltage goes from we now measure a different voltage of, let's say, 6.3 volts. Again, we measure. Whereas before we measured 5 volts, all of a sudden we're measuring 6 volts. Now, if we're measuring 6 volts here, all of a sudden, something about the circuit has changed. We know what's changed. This resistance has changed. So now we will repeat the process. We'll say, okay, I think what's happening is, I think you're guessing, that the temperature has changed. Because the temperature has changed, the resistance has changed. Because the resistance has changed, the voltage has changed. But what is the new temperature? We once again need to go apply this equation and then this equation, right? So, you know, you can see how when we're doing this process, we're almost going in reverse, right? We have these equations, right? But we're running the equations in reverse. So let's go through it. All right, 6.3 volts. Well, that has to equal, we still have this equation, R sub T over R sub T plus 1 ohm. This did not change, and neither did the fact that we have 10 volts here, right? So what is R sub T in this situation? Chosen to be not so complicated. What R sub T here would go from 10 volts to roughly, roughly 2/3 of 10 volts.
2, because you said 2/3.
2 ohms, would that work?
2/3. It would be point.
Oh, maybe I should have said 6 point, what is it, 7?
Yeah.
What's that? Well, let's leave it at 6.3, it's fine. What would be the resistance at 6.3? Someone want to do the calculation? I don't have a calculator up here. Close to 2.
6.6 on it.
6.6 ohms. All right. So the resistance now is 6.6.
No, that's if the resistance is 2. That would be the voltage.
Oh, then it would be 6.6 on and on. Yeah, okay.
Sorry.
All right, let's make our life simple. 6.6 volts, which is what I was aiming for, all right? Giving us a simple calculation that the resistance is now 2 ohms. But this is not quite enough, right? The question is now, what is the temperature, right? In order to do that, we need to go back to this equation here, right? Which, again, we could have removed this one here. We could have removed this one here, right? So if the resistance is now 2 ohms, what is the temperature that must correspond to? Right? We sort of need to, we have 1, right? We need to sort of increment that, right, by another 1, right? So we need this to equal 1, right? And so the temperature now is 26 degrees C, right? The temperature went up, right? Ignore this. This was just a hypothetical, right? In this case, the temperature, and it kind of makes sense, right? I mean, it's 1 ohm per degree C, right? And so we went up a degree C, we went up an ohm. All right, so now we have a situation where the temperature is 26 degrees C. How did we know that? We knew that from the instrument. By the same logic, if the temperature went to 32, right? If the temperature went to 40, we would be able to detect that by a change in voltage, right? If you want to know whether your brother has a fever, you can ask him, right, to grab onto this resistor, measure the resulting voltage, calculate the resistance, and then from the resistance, calculate the temperature. We see, however, for this process to work, you need 2 things. One is the equation for the circuit, and the other one is the equation for the sensor. Right? And this will come up again and again. Right? We can't do this process without it, which is why if I'd given you a thermoresistor and I hadn't given you an equation or hadn't given you the parameters, you'd be stuck because you wouldn't be able to do this calculation. You'd be left with too many unknowns. Now let's reconcile this picture here with the picture up above. So we started by reviewing the parts of all biomedical instruments that do measurement. And I said, no matter how complicated it looks, right, it has a sensor with a wire and a circuit and a display, right? And before we put that, right, into these terms, right, let's go back to the example of the pulse oximeter. When it looks like this, and this is connected to an instrument, it's pretty clear what's going on, right? This must be the sensor. We'll learn how this type of sensor works is. This is the cable, at least 2 wires, maybe more in it, right? And then this plugs into a device where there's a circuit and there's a display, right? So remember, one of the goals of this course is allow you to look at an instrument and not be overwhelmed and break it down into its components. Okay. Now, this doesn't look like that, does it? Right? I mean, there's no cable. Right? So you'd say, well, this seems to break the mold, but I just said it doesn't, right? It doesn't break the mold, right? It's just that the cable is very short. Now, I have to put my finger in here for this to work, right? I can't put my finger here. I can't put my finger here, right? Just like with the temperature device, right? We understand that there's a very specific point that needs to contact the body. That point we know has a name. It's called the sensor. And in this case, right, you know that the sensor is somewhere in here, right? And again, we'll fully describe how a pulse oximeter works later in the course. For now, just accept that there must be a sensor in here, and that's where the finger goes. And then there's a very short cable, right? And then there's a display. Yes?
So the sensor would be the fixed resistance?
Exactly. So in this case, it's a fixed resistance, right? In this case. But I want to finish the analogy with this. So you understand that this does not break the rule. It does not break the rule. Let me show you another pulse oximeter. So my watch, right, is now going to measure my blood oxygen level, right? It's going to take about 9 seconds, right? That's interesting. That seems a lot like that. What a clever little invention, right? If I don't move my hand too much, it'll give a reading. No, unsuccessful. I moved my hand too much, all right? But it could have worked. Now, you have to reverse engineer it, right? There has to be a sensor, right? I said there has to be a sensor. There's a sensor, there's a display, and there's a very short wire. And there's a circuit inside. It's the same principle. Now, of course, this can do other things as well, right? But it's the same principles for all instruments, even when they don't look the same. All right? So that was our general principle. So now, let's go ahead to the device that you designed, right? And this is your design, right? So this should also work. And let's warp it into this principle. And to do that, I think the clearest thing to do would be to simply redraw this circuit. What I'm going to do is I'm going to put the R sub t here. And this is a resistor, so it has 2 ends, right? So to combine that in a circuit, I need to connect both ends. So I'm going to take these ends, and let's say I just kind of wind them together. I'm going to wind them like this. All right? And now I have another part here. I'm going to call this the circuit. Let me do this. Here's E. Here's R sub 1. Now I'm going to take the voltmeter, which has a display on it, and I will connect that voltmeter, to be very clear, to this point here and that point here, right? Voltage must always be measured between 2 locations. And so now I've taken this, I didn't really change it, I just kind of twisted it around a little bit. And here is our wire, or if you want to call the cable. Now, one thing that's nice about this is I can make this wire as long as I want. All right? I can make it this wide long, I could make it even wider, right? So what you could have now is you can have a situation where this is on the table, and there's a wire that comes out, right? And you just ask your brother to please grab onto the end of the wire, right? You can bring the wire to him, right? There's no a reason why you can't make this as long as you need to make it. And so now what we've done is we've taken the first instrument that we've designed in this class, a temperature measurement device, and we've converted it into this form. Now, there is perhaps one thing that you still find unsatisfactory, and that is the fact that this display is reporting voltage. And that seems rather inconvenient. You would rather that it report temperature, right? Now, to do that, we need to get to something else in this course, right, where we're probably going to be digitizing these signals and converting it. But for now, you can get from this voltage to temperature. And the way you do that is you have to go through the circuit equation, and you go through the sensor equation. And then you get the temperature, right? So you need a calculator, right? Or maybe it's an Excel sheet, and it has all the voltages in one column and all the temperatures in the other column, right? So you can just look it up. It's functional, but perhaps not as satisfactory as you would like at this stage. Any questions on this? Okay. Okay. Yeah.
So for things where, like your watch, right? You said it does many other things as well. But there might be some devices where you have the same sensor, but they go to different things. Would that division usually happen by the wire or to the display or the circuit?
The question is, if you have one sensor, can you send this signal to different locations? In principle, you could, right? You could, in principle, split this wire. In practice, I think what you would do is you would probably process it first, and only after processing it would you distribute it. And as we go through the course, we'll talk about why that is a preferred method.
Okay.
But that is actually a good circuits question. Okay.